Okay, to end this module, let's just see where we're at so far with this course. So we've learned quite a few problem-solving techniques. And so to recap, we have our 1D motion, and that's with constant acceleration, so we can use our kinematics equations, or without constant acceleration, so non-constant acceleration, we have to use calculus. And then we have the same thing in 2D motion, constant acceleration, or use calculus, non-constant acceleration. Then we did Newton's second law, and I've divided it up here just because the next module we're going to be focusing on just Newton's second law with circular motion again. But Newton's second law with straight line motion, so that's just when we solved for, say, a linear acceleration A. And then we had Newton's second law with circular motion, where all we did was say that A was v squared over r. But really our Newton's second law problems, you draw a free body diagram, you do the sum of forces, you set it equal to ma. Then, previous module, we learned about the work kinetic energy theorem, which was if you had a force that depended on position, then we could actually then analyze those situations. And then in this module, the main problem-solving technique that we have used is the conservation of energy, which we have, which I will often refer to as just COE. And then the other thing that often shows up is the force and potential energy relationship. So that's another problem-solving technique. That was going to be the one where we had the f sub x equals minus du dx. So those are the two ones that showed up from this module. Conservation of energy is a big overarching, fundamental principle, and the force potential energy relationship is one that allows us to understand what potential energy is in terms of a force and analyze potential energy diagrams, etc. Okay, so when we have problems then that you have to analyze, a lot of times you have to take a step back and say, okay, which of these can I apply to my situation? And knowing, how to identify them. First, is it 1D or 2D motion? Is my acceleration constant or non-constant? Am I given information about my forces, in which case I'd want to use Newton's second law if I have to draw a free body diagram, or maybe I'm given a function or some information that allows me to do work kinetic energy. So kind of use this as a checklist. Which one of these might apply to your problem? If you're looking at a problem and you're stuck, think, does this apply? Does this apply? Does this apply? And then you'll get better at it. It's a skill that we develop. This is one of the major critical thinking, problem-solving skills that you get from this class. In terms of conservation of energy, remember you have to have like a start and an end. And very often there might be a change in height involved. Or you might have, some amount of energy lost for friction. So a good example of just combining the previous module with this one is you might have something where, let's say it's traveling along a level road and you're applying a force, f sub x, and f sub x is given as some function, say ax squared, and then that acts until some position, here, let's call this x2, and let's say it starts at x1 and it's at rest, and you apply that force. And then after you apply the force stops acting, and then it might travel through a rough patch with some coefficient of kinetic friction mu sub k, and so then eventually, it travels through, and then it might come to rest. And the question is, how far does it travel through the rough patch before coming to rest? And this is a two-part problem. In the first part, you're going to want to use work, right? So this will give you the work kinetic energy. And you can get little notations for these as long as they're clear, so you don't have to write out the full name every time. But this would be work kinetic energy, and you would use work kinetic energy to get the speed at x2. So that'd be the speed then heading into the rough patch. And then over here, this is fairly straightforward. You can do it a long way with Newton's second law and 1D motion. Much easier to just do conservation of energy. You start off with some kinetic energy initial, all turns into it when it stopped, would all turn into delta U internal because it stops. So you had some initial kinetic energy at x2, right? There's some energy here. and then your final location would be where it stops. So you do conservation of energy, and the goal there would be to get the length that it traveled in the rough patch, because it would have the same kinetic energy as x2 that it had going into the rough patch, didn't slow down. So two-step problem, work kinetic energy, allows you to get the speed, and then you can use conservation of energy to get how far it went before it stopped. And that's just one example. I could apply the force, but then I can have it travel up a hill and hit a spring, and I have a conservation of energy that way as well. Or you could imagine that I could relate all of these to 1D or 2D motion. I could apply my force, my work. Maybe I apply my force on the object, F sub x. It acts for some distance here. And then maybe it travels through a rough patch, so it loses some energy, but it still keeps going so that it then flies off the end of a table, right? So maybe you're given the length of the rough patch, maybe it has some UK, it goes here, and then it flies off the table, and you have to figure out where it lands. So now all of a sudden you have 3 parts to your problem, right? You would have work kinetic energy, you would have conservation of energy, and then you would have 2D motion. So then you would do a 3-part problem. So identifying each part, we know the starting points for each part, and then just executing them. You don't always have to see the finish line in order to start the race. Same thing with problem. You can know that you're taking the right steps and do that for each step of the problem, and you will get there. Let me know if you have any questions at all about this module.